Good morning, students. Students, will continue with our laws from the chapter States of Matter. We have done all the types of laws like Boyle's law, Charles' law, Avogadro law, and by combining all these laws, one equation comes that is ideal gas law or ideal equation, right? Before understanding what do you mean by ideal gas equation, first of all, we'll consider the ideal gas. An ideal gas is a theoretical gas or an imaginary gas composed of a set of randomly moving, non-interacting points like particles, and they obey the gas laws always. An ideal gas is an imaginary gas that obeys gas laws under all the conditions. Right, students? And what was these gas laws? We'll consider it once again. From ideal gas equation, the first law was Boyle's law. The second law was Charles' law. The third was Avogadro law. So when we combine all these laws, which states that V is inversely proportional to P, V is directly proportional to T, and V is directly proportional to number of moles. So all these gas laws come under all these laws comes under the gas laws, and while combining these laws we'll get an equation which is known as ideal gas equation. And students, ideal gas is that gas which obey the ideal gas equation. So according to ideal gas equation, we'll get a relation that is PV is equal to nRT, which I've already discussed with you, but still I want to just tell you again so that you can understand the concept clearly. So PV is equal to nRT. Here, this ideal gas law relates with the various macroscopic properties such as pressure, volume, amount of matter in the system, and the temperature of the system. And here, P is a pressure whose unit is Pascal or atmosphere, already discussed with you, and V is volume, which must be in liters or meter cube, and N is a number of moles of gas whose unit is mole, and 1 mole is equal to 6.023 into 10 raised by 23 particles, ions or molecules. Whereas T is the temperature which must be in Kelvin or degree Celsius, and R is a universal gas constant, and at STP, standard temperature pressure, whose value is 0.0820 liter atmosphere per mole per Kelvin. Or we can take in a SI unit is 8.314 joule per mole per Kelvin. Right, students? Now, Maxwell-Boltzmann distribution for ideal gases. Maxwell distribution give us about the distribution curve of speed of molecules. So to find out the speed of molecules in a gas which is at the fixed temperature, one scientist was there which is known to be Maxwell Boltzmann, who gave the distribution curve for the ideal gases. And this distribution function can be used to find the most probable speed, root mean square speed, and average speed of the molecule. We'll discuss what do you mean by root mean square speed, most probable speed, and average speed of the molecule. See, he plot a graph between the number of particles and the molecular speed. As we can show, we can see that it is being shown. And to mention the distribution curve does not give us the speed of individual molecule. Rather, it shows us what fraction of molecules are having a particular speed according to him. See, now Maxwell-Boltzmann distribution curve give us about the three important parameters. First is the average speed. The average speed possessed by most number of molecules. And average speed accounts for the most relatively large number of molecules. Still a lot of molecules that have speed greater than average speed, which is given by this formula. And root mean square speed means these are the different types of velocity, students, right? So we must know about these velocities. these velocities just tell us about the speed, right? Molecular speed. So the speed, average speed is the average of speeds of different molecules in a gas at a different or a particular temperature, right? And root means square speed. As a name suggests, it is the square root of means of the squares of the speeds of different molecules in a gas at a given temperature. As it is shown by the formula, right? That root mean square is equal to under root 3 PV upon M. Here P is a pressure, V is a velocity, and M is a mass, molecular mass. Now, the third parameter which is being given by the Boltzmann, that is most probable speed, and it is a speed, right, which is possessed by the maximum fraction of gas molecules at a given temperature. Clear, students? These are three types of parameters which was given by Maxwell distribution of speeds and which explain us about the effect of temperature and the molecular speed, the relationship between the speed and the temperature, right? Now, after that, we'll come to on kinetic theory of gases. Students, we know that why a gas can be compressed, right? And what are the properties of gases? So basic properties of kinetic gases, we know that every gas consists of a large number of very small identical particles known as molecules. Right, students? Kinetic theory connects the large to the small. It describes the macroscopic properties of a system like temperature, pressure, viscosity, electrical conductivity, and volume in the terms of molecular composition and motion. And it describes the gas or the collection of large number of submicroscopic particles, right? It also explains the randomness arises from their many collision which each other, like gas collide with each other. So it relates the collision of gases also. There are some key points. Gases consist of a large number of molecules that are in a continuous random motion. The combined volume of all the molecules of a gas is negligible relative to the total volume in which the gas is contained. Student, this point is very important. According to the kinetic molecular theory for gases, that volume occupied by the gas is negligible as compared to the total volume of a gas. That's why gas can be easily compressed. But this postulate was later on it was wrong, right? We'll consider it. Please note that. The second point was not correct. Afterwards, it was being discovered that second point was wrong. And the third point, that is attractive and repulsive forces between gas molecules are negligible. But that is not true again, right? The collision of the molecule with one another or also with the walls of container and are perfectly elastic. This means there is no loss of energy during the collision. That was correct. The average kinetic speed of the molecule is directly proportional to the Kelvin temperature. That was also correct. Only out of these few postulates, only these two factors are wrong, right? Which we'll deal in our later topic. Now, what is a reason for the deviation of ideal behavior? Students, we have two types of gases. One is ideal gas and the another is real gas. An ideal gas is that gas which obey all the gas laws under all the temperature and pressure, right? And a real gas is that gas which do not obey all the gas laws at all under all the conditions of temperature and pressure. So, why an ideal gas and what is unreal gas? When ideal gas deviate from its path, it becomes a real gas, right? How it deviates and how it becomes a real gas? When it is being obeying all the gas laws under all the condition and temperature, and it is being obeyed, PV is equal to nRT. It is known to be an ideal gas. But when this ideal gas do not behave this gas laws at under or all the temperature and pressure, under all the conditions of temperature and pressure, it becomes a real gas, right? And this is because of two reasons that ideal behavior show the deviation. Which two reasons was there, which two assumptions of kinetic theory was wrong, which I have told you in my previous slide, that two assumptions was wrong, right? What was that assumption? The first, the actual volume of the molecule is negligible as compared to the total volume of the gas. And second, there is no force of attraction between the gas particles. These two postulates was, or these two assumption of kinetic theory of gases was wrong. Because of this only, the ideal gas deviate from its path and becomes a real gas. So, students, what are real gases? A gas which does not follow ideal gas behavior under all the conditions of temperature and pressure. That gas is known as real gas, right? So, real gases do not obey ideal gas under all the conditions of temperature and pressure, and this can be understood by plotting a graph between PV against P, right? Now for ideal gas, the PV is constant for any pressure. So graph obtained is a straight line, as you can see in this graph. It is parallel to the pressure axis, but for real gases, it's not parallel, it's not a straight line. We can see the different behavior, the positive deviation as well as the negative deviation. If the deviation is above the axis, that is called a positive deviation, and it is, if it is below, it is known as negative deviation, students, right? How this positive deviation, negative deviation being decided? By the means of one factor which is known as compressibility factor. So for ideal gases, students, Z is equal to 1. Z stands for compressibility factor, right? And for real gases, Z is not equal to 1. It may be greater than 1 or smaller than 1. Here in this graph, it is being shown that for H2 and helium, PV increases with the increase in pressure. And for CO and for CH4, methane, the value of PV first decreases and then reaches minimum value and then increases. And this behavior can be demonstrated by one factor known as compressibility factor. So students, for ideal gas behavior, if compressibility factor value is 1, right? But for real gases, it is not equal to 1. It is either greater than 1 or it is smaller than 1. Clear? So compressibility factor just show us about the deviation of ideal behavior. The deviation from the ideal behavior can be measured in terms of a compressibility factor, which is represented as Z, and which is a ratio of product PV and nRT, right? So mathematically, Z can be represented, Z is equal to PV upon nRT. So students, if Z is less than 1, it means the gas is more compressible than the expected from the ideal gas behavior. And this type of behavior is known as negative deviations, right students? And which is shown by the gases such as CO2, methane, and nitrogen. And if Z is greater than 1, this indicates that gas is less compressible than the expected from ideal gas behavior. And this deviation is known as positive deviation. And the gases H2 and helium show this type of behavior, right? This is very, very important, that what do you mean by compressibility factor, and what do you understand if Z is greater than 1 or less than 1 or equal to 1. If Z is equal to 1, it is ideal gas, and if it is not equal to 1, that is, it is greater than 1 or less than 1, it is known to be a real gas. So how much deviation has been occur can be measured in the terms of compressibility factor. Now, here we have the difference between ideal and the real gases. So students, just recall again, ideal gases obeys all the gas laws under all the condition of temperature and pressure. Real gases do not or does not obey laws only at, or we can say does not obey the laws, or we can say obeys laws only at the low pressure and a high temperature. One condition is there. Ideal gases, in ideal gases, the volume occupied by the molecules is negligible according to kinetic theory of gases. So ideal gases is based upon the kinetic theory of gases. The volume occupied by the molecule is negligible as compared to the total volume occupied by the gas. But according to real gases, this assumption was wrong. The volume occupied by the molecule is taken into account and it is not negligible. According to ideal gas, which is based upon kinetic theory of gases, the force of attraction between the molecule is negligible. But again, this assumption was wrong, which is being corrected by real gases. The forces of attraction cannot be ignored at the temperature and pressure. It obeys the ideal gas equation. It obeys the van der Waals equation. So, what happened? Some correction has been added in the ideal gas, and when correction is being added into P is equal to nRT, a new equation arises which is known as van der Waals equation, which is being given here, that is P plus an square upon v square, v minus nv is equal to nRT. Here we have added some correction factor, we have added some constant in this P is equal to nRT equation, and the new equation becomes the van der Waals equation. Here the correction factors are A and NB. Thank you so much.